This video is part 2 of section 3.5, Symbolic Arguments. In the previous video, we were discussing how to determine whether or not an argument was valid using the following, scrub a little bit more, this up here. Okay, so in other words, you have to write in symbolic form first, construct a truth table, and then determine whether or not it's valid by using this number 3. If a conclusion is true and every row of the truth table of the premises are also true, then the argument would be valid. Otherwise, it's false. It's invalid. Also, if the conclusion is false and those two premises are still true, it is still going to be invalid. Okay. So if we go down to this example, we're going to go ahead and run through how to do a truth table with an example. So notice that we have not P and Q. So again, this is our first premise, this is our second premise, and this would be the conclusion. Okay, so we're going to start by starting with our normal P and Q. And we're going to go all the way across just like we usually do because we don't know how long it'll be. So let's go ahead and do that real quickly. Okay, so just like we have in the past, we're going to go ahead and fill this out with our possible combinations. So we have that these can both be true. We can have this one true and this one false. We can swap them. And we can have that they're both false. Okay. Now, after that, we're going to go ahead and start with the premises and see if we need to do any additional columns here. So it looks like our first premise is not P and Q. So for this statement, we have Q, so I can look at that one right away. It's right here. And we do not have not P, so I'm going to have to do not P as well. So let's go ahead and do that in a different color. Let's do that right here. Let's do blue. So we're going to do not Q, I'm sorry, not P right next to it. And we would be looking at our P for that. Okay. So again, the reason I'm doing not P first is because I need it for my first premise. So not P would be the negation of P, which would be the opposite of everything that's in here. So instead of true, we would have false, false, true, and true. Okay. And now that I have not P, I can go ahead and go back and look at my first premise. Remember, this is my first premise here, which would be not P and Q. So for this one to be true, remember that an and statement, okay, that little upside down V, both have to be true. Both true would be a true, okay? So that means I'm going to look at each one. So here and here we have a false statement. Here and here, both false. Here we have two T's, so that's going to be true. And then we have a false. So it looks like we only have one area where it's true so far, okay? And finally, we're going to look at our conclusion. So the conclusion is just Q again, which means all I have to do is look at Q and copy paste it. So true, false, true, false. Okay. And at this point, just like I did in the example before, I'm going to look at my premises and my conclusion, which would be this box right here. Okay. This was my first premise. This is my second premise because that's what's right here. Okay. And this one is my conclusion. Okay. This would be the conclusion. Okay. So I'm looking for a row that has all true. Okay, so let's see what we got here. This has false, false, true. So row 1 is out. Okay. Oops, something happens. Let me see. All right, so again, this one is going to be out. Okay. The second one has false, false, false. So that one is also going to be out. My third column has, I'm sorry, third row has true, true, true. So this one might be it. Okay, but let's just double check the last one. False, true, false. So it's out. So it looks like row 3 proves that it's a valid argument. So valid arguments by row 3. So just make sure that when you do your examples or your homework, that you do show all this work. Because if you tell me it's valid or invalid, but you don't provide any proof, so I don't see any truth table, then unfortunately you're not going to get credit. Okay, so just make sure that you do go through this. It does look like a lot of stuff to write down. So if I lost you anywhere, please feel free to contact me and let me know so I can help you out. Okay, we're going to do a couple more examples that are going to be a little bit easier. So here we have a chart, I'm sorry, a table, and it can also be found in your book. It says the standard forms of 4 valid arguments. So you're going to like this one because this one does not require any truth tables. Yay, no truth tables. So as long as we have one of these forms, okay, in a argument, we can automatically say it's valid because of the law of syllogism or whichever one it falls under. Okay, so we're going to go ahead and go right into an example so you can see how this works. We have he will attend Stanford or Yale. So some guy is going to attend Stanford, let's call that P, or Yale, let's call that Q. And notice that we have an or in the middle. So this would be that V looking thing. So right off the bat, my eyes are going to go to this one because I see that the or statement is right there. So let's see if it is that one indeed. It says he did not attend Yale. So he did not attend Yale. So that has something to do with Q, but it has that not in there, so it'd be not Q. Okay. Therefore, so there's my 3 dots right there. He attended Stanford. So there's my P. All right. So let's go ahead and write this out with proper notation now. So we have P or Q. So P or Q. Okay. Then we have not Q. And then we have therefore, so dot, 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 Stanford. So let's see. It does kind of look like this one. So I'm going to go ahead and say that this is a valid argument by this disjunctive syllogism. Now, some of you might be a little confused because this has the not P and then Q, and this is backwards. But if you think about it, P or Q, so this right here is the same as Q or P. We can swap them. It does not change the value. So if I swap them, they would land in the opposite spot anyway. So this is going to work. So this is valid by disjunctive syllogism. So this would be our justification, okay? And this right here. We're going to go ahead and do one more example that does the opposite. So these are 2 forms of invalid arguments. So in this one, we have 2 forms that show us right away it's not going to be valid. And these are called fallacy of the converse and fallacy of the inverse. Okay, remember that converse is just swapping. It would be like Q implies P. Okay, and the inverse is doing the opposite. It's saying not P implies not Q. So we're kind of working with those 2 ideas to prove that these are invalid. Okay, so let's see. We have if it is a dog, so if it is a dog, let's call that P. My mouse is messing up again. So this would be P, okay? Then it has fleas. So we have a then right there. So I'm going to go ahead and circle that because that looks like it's going to be an arrow. Okay, and then it has fleas would be our Q. So then we go right into it has fleas. So there's Q. Therefore, there are my 3 dots. It is a dog. So therefore P. So let's go ahead and write this all out. So we have P implies Q. Okay. Oh, wrong color. Q. Okay, I'm going to scroll down a little bit just so I can write this nicely. And then we have Q, therefore P. Okay, so this is what our symbolic argument looks like. Let's see if it matches either one of these. It looks like it matches This one, exactly. So this would be invalid by fallacy of the converse. Fallacy of the converse. And that's it, guys. That's your method of finding if something is invalid without a truth table, okay? And also the one before where it's valid without a truth table. If you have any questions, let me know.